Yeah. So today I will quickly finish the summary of last semester, last session. This will be very quick, and then we can start the new part, the new material. Okay. So last time we finished with the notion of Frobenius theorem dimension. And I said, so last time we finished with the notion of Frobenius theorem dimension. And we defined the fusion matrices. Fmx given by the fusion coefficient of the left multiplication, and we take the transpose for the associativity of the fusion ring being equivalent to being this representation of the fusion ring. Okay. So the theorem now is the following. So the Frobenius theorem dimension, what we call that FP team. So the theorem is the following. The FP dim of X. So we call that X is in the basis of the fusion ring. X is in the basis of the. We talk about Z plus ring of the ring. Yeah. So this Frobenius theorem dimension is nothing but is a positive eigenvalue of the matrix Mx. In fact, the maximal one. So in other words, Fp dim X is equal to the matrix norm of Mx. Because it's a well-known result in linear algebra, the matrix norm is if the matrix has positive eigenvalue. Let me check. In this case, it is a matrix norm. Anyway. In fact, for this matrix norm. Okay. So the proof of that, let's put that in parentheses. The proof of that is due to Perron and Frobenius. So I will not put the proof, but just this is quite old. So this is due to Perron in 19, find this date, and Frobenius 1912. So want to see the details, see the book, section 3, details about that. So what is important here for us is to note that it provides a notion of dimension which is not necessarily integral. Not necessarily integral, but still algebraic. It's not an integer. It's an algebraic integer, but not an integer in general. Okay. And so the next theorem say that in fact it has the good property of expected for a dimension as follow. And by as follow, I mean the theorem saying that this is induce, in fact, by linearity, induce a ring homomorphism. By linearity, because we know that the ring is a free ring, the free Z module generated by the basis. It's a ring homomorphism. It's a ring homomorphism like that. Such that where with FP of B included in 0 infinity, the open interval. So this this is due to positive eigenvalue. This is a positive for the basis. For the basis, not for the ring. For the ring is just the ring is a free Z module, so you can by linearity you can have also negative stuff, but for the basis it's positive. Okay, so we are almost done for Frobenius-Perron dimension. So I will erase this line. Okay. So can I put it like that? Okay. So now so now we defined. So last time we said that if you start from a ring category with left dual, the Grothendieck ring is what we said, a transitive unital Z plus ring. And the Frobenius parent dimension was defined for transitive unital Z plus ring. So sorry for not being able to finish that last time. It's a bit discontinuous, but so according to previous theorem, previous proposition. So by previous proposition, I'm talking about the fact that the Grothendieck ring of a ring category with left dual is transitive unital Z plus ring. Sorry, I should have that last time, not today. So according to this proposition, we can talk about a Frobenius parent dimension for a finite ring category. Not only ring, but ring category. We can talk about Frobenius parent dimension for a finite. We need finite because we need a finite basis. Ring category with left dual. So the tensor category. Tensor category. Finite tensor category. So finite tensor category. So we prove in some previous proposition that the finite ring category with left dual is rigid or something like that. I don't remember. So in fact, this assumption implies that it's also a tensor category, if I'm not mistaken. Some previous proposition. Okay. So we have this notion of Frobenius parent dimension given at the ring level can go to the category level. So this is a very, very important tool. And in fact, it works, as you can expect, for the usual example. The usual example, you take the category of representation, the complex representation over on a finite group of finite. So we take over the complex field representation of G finite group. Then, in fact, it's easy to check the Frobenius parent dimension of a representation X. Maybe I should write V. Is exactly the complex dimension of V. So in this case, you exactly recover a vector space dimension. It is integral here. But as I said, in general, that can be non-integral. This is still finite, but non-integral. It's always an algebraic integer, but not necessarily an integer. In fact, we may prove later, if we have time, that this is a cyclotomic integer. Okay. So that is the end of. This is the end of the summary part. Now we can start new part. Summary part. Let us start. New part. New material. New material. Some new materials. Okay. And the new material today will be, in fact, will be related to the notion of dimension, but not now, no more the Frobenius parent dimension, but the quantum, the categorical dimension. There is you can define a notion of dimension at the level of category, and this dimension is not necessarily the same as the Frobenius parent dimension. In fact, when it is the same, the category is called pseudo-unitary. So we will. So the title of the new section is, in the book is called Quantum Trace, Pivotal and Spherical Category. So in this section, in this new section, we will meet a new notion of dimension, another notion of dimension, and other notion of dimension. So sometime called categorical dimension, which is different from the Frobenius parent dimension, in general. Now, but if these two notions if these two dimensions are the same, so if the categorical dimension is equal to the Frobenius parent dimension, so if these two dimensions are the same, these two notions of dimension are the same, then the category is called pseudo-unitary. So this is just an introduction part to connect with what we just finished. We will not talk about pseudo-unitary category now, but in fact, let's mention that, not that, there exists a notion of unitary fusion category or tensor category. And not that unitary imply pseudo-unitary. So in fact, the unitary category are the unitary coming from analysis, in fact, coming from subfactor theory. Pseudo-unitary. Any unitary fusion category is a fusion category of a subfactor. Anyway. So it's still the introduction for people who are interested in fact, in physics, we mainly meet unitary fusion category. And the fusion category of a subfactor is always unitary. So I did not define what is unitary here, but in fact you can understand unitary as something in fact you can meet in physics, in fact, in physics and in analysis. Anyway, so this is the end of the introduction part. So yeah, anyway, end of the remark. It's a big remark. Okay. So what this is about in details. So it's not only about dimension, but we'll know notion of trace, notion of pivotal and spherical categories. So what time is it? So what about the notion of trace? So definition. Let's see, be a rigid monoidal category. So now we come back to monoidal category. So we will mention also tensor category, but what we will define now can be defined at the level of rigid monoidal category. We don't need K-linearity structure. We don't need tensor category. So monoidal category, you take an object, V, and you take a morphism between V and its left dual. So you define the left trace so I have something in mind I want to mention also, is that up to recently, we did not know whether there exists a fusion ring admitting a categorification without unitary structure. So we did not know, we did not know the following. So you have a fusion ring And you have a fusion ring admitting a categorification in general, so it's a Grothendieck ring. And we did not know whether this Grothendieck ring admits a unitary categorification. So that was found. That was found recently. In fact, someone made something which admits a categorification, but not a pseudo-unitary categorification. So in particular, not a unitary categorification. But up to now, everything was more or less unitary categorifiable. If something was categorifiable, it was unitary categorifiable, but we now know some counterexamples, but they are quite rare. But of course, from this example, you can make an infinite family, but randomly, for small rank, etc., this is quite rare up to now, at least in the literature. So, okay. So, what is the left trace? The left trace is defined as follows. So I will provide a purely categorical algebraic definition, and then we will give a pictorial. As usual, we will give a pictorial definition for the intuition. So the left trace is defined as follows: the left trace of this morphism. So trace left will be an element of the endomorphism. So this will be an element in end C. So this will be a morphism between 1 and 1. And we know that in some good case, this reduced to the scalar, but in general, it's not the scalar. So this will be from 1 to 1. So it starts from 1, and you apply the co-evaluation map of V, and you get that V tensor V star. You apply A on the first component and the identity of V star on the second component, and you get, so you get something I forgot here, it's double star. Sorry, so we get V double star tensor V star. And you apply, now you can apply the evaluation map on V star, and you come back to 1. This morphism from 1 to 1 is called the left trace of A. As I will explain later, for tensor category, this can be interpreted as a scalar, but in general, it's not a scalar. So what is this is a picture. So you have a morphism A between V and V double star. So you make the picture like that. You apply, so you have the evaluation, coev here, coev, and here you have ev of V star. So, and here you have V star. So you can see, pictorially, trace left of A is equal like that. So, yeah. In fact, this is usual. In fact, the trace in pictorial representation of a category or in planar algebra, it's always something you close. You close. Okay. And so this was a left trace, but you can define a right trace. So you can define a right trace. Time is it? With So for the right trace, you need another morphism with A in OM C V, the double right dual of V. Here, you see this is not the same. Here it's double left dual, double right dual. Okay. And you define the same. So now I will put the details, so I will write also for the right case. So trace, in this case, always it's still a morphism from 1 to 1. So you apply co-evaluation of the right dual of V, and you get right dual of V tensor V. You apply here identity of right dual of V tensor A, and you have right dual of V tensor double right dual of V. And finally, you apply the evaluation map on the double right dual of V, and you come back to 1. And so you have the same analogous picture as follow. So you have a picture. You have A, so trace right of A equal. You have the morphism A between V and double right dual of V, starter V. And now you go on the other way. So here, you have the co-evaluation map by the same. You put the co-evaluation map, and here co-evaluation map and evaluation map, this one and this one. This one. So co-ev of star V and ev of double star V. Okay. So trace. So you close. Here you close. So that's strange, in fact. The left trace, the right trace. So you close on one side, and here you close on the other side. So I realize that here you close on the right for the left trace, and here you close on the left for the right trace. So I hope I did not make a mistake, but I don't think so. But anyways, let me check. I don't think I made a mistake, but it doesn't matter. If I made a mistake, you just need to switch the one and the other. In fact, this is completely symmetric. Everything you can do for the left, you can do for the right. The pictorial like that. Yeah, should be like that. Yeah, anyway. So, what about now? Yeah, now this is a remark about what is the relation between such a trace and the scalar, because in fact in linear algebra, a trace is in fact the trace of a matrix is a scalar. It's an element of the field. So it's not true in general here, but it's true in some usual case. So remark. So by definition, the left and the right trace are in the endomorphism, the more between 1 and 1. So be careful here. This is not the same A. I may use another letter for that, maybe to not be confusing. Let be. If you want. B. Okay. So there is a morphism between 1 and 1, but we know that in a tensor category C over a field K, the homomorphism between 1 and 1 is this set is isomorphic to the field itself. It's one-dimensional. So the trace, left or right, can be seen as a scalar, an element of the field. And this is fundamental. In fact, for example, for a categorification problem, we reduce to solve pentagon equation, and the variable are F symbol, and these F symbol are, in fact, element here. So they are scalar, they are element of the field. If we are in a tensor category, if you are in a multi-tensor category, it's not an element. It's not an element of the field. Maybe you can see that as maybe as a matrix, or I don't know. But it's not an element of the field. Okay. So now let us provide some property of the trace. We will provide a list of properties according to what is the relation between left and right trace, how the trace deal with the direct sum, with the tensor product, and some other property. So we will not prove all this list in detail, but we will prove some of them with some picture, and we will leave some other as an exercise. So proposition. Proposition. So let VW be two objects of a rigid monoidal category C. You take, as above, you take a morphism between V and V double star. And now B is a morphism W and W double star. So B is not the same as the B above. So be careful, it's not the same B. So first property, the left trace of A is equal to the right trace of A star. And in fact, A star, you will see that in fact A star has a good property for being traced by a right trace. Second property, so if C is additive, then it's additive category. To have a direct sum, the direct sum is equal to the sum itself. That's okay. That's good property. The third property about the tensor product. is just the product. And these two, we have the same for trace right. And the last property. So if you have a morphism from V to V, then the left trace of A composed with C, but in fact we can just write AC. We don't write the composition symbol, is equal to the left trace. In fact, you can. In fact, in matrix, in linear algebra matrix, the trace of two matrix AB is equal to the trace of BA. You can commute. Here, you can almost commute. In fact, you need to take the double dual. Trace of AC is trace of C double dual A. And the right trace of AC is equal to the right trace of double right dual of C. So it's really, in fact, this notion of trace has all the good property of what you can expect from a trace, generalizing the trace of a matrix. Okay. So what time? So it's time for pause. So remark. This then this notion of trace as all property for being a good generalization of the trace of matrices. In fact, you can make a category in which in which this trace is exactly the trace of matrix. But anyway, so pause. So pause. Pause. Okay.
Record.
Okay. So proof. 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 What about the first point? So the relation between the left and the right trace. So so let us prove. Let us prove one by picture. So you take the morphism A from V to the V double star. Then the A star, the dual of homomorphism, as we saw at the beginning of the summary part, is like that. So V double star, here the V star, and here V triple star. So this is a bad picture. Let me draw something better. Like that. Okay. A V double star, V star, V triple star. So now, now we will apply the right trace on that. So you take U to be the double dual of V, then we know that the double right dual of U is so V double dual. We know that we can take a triple dual, the triple dual. So this is like that. We know that so if A equal B star, then B equal star A. We can play between left and right dual. We already mentioned that. So if U equals the triple left dual of V, then the double right dual of U is V star. So now you can apply the right trace, because for the right trace you need right dual. So the right trace of A star is, so you have A star, and now you have like that. So U double star U star U. But this is equal to so now you can write A star. You can write you can put this in this box, and what you get is the following. So you have A here, and you have like that, and then you apply the right trace, like that. Okay. So yeah. So here you have V star. Here you have V triple star. But what you can apply here, recall that we can apply the zigzag relation. Zigzag relation. Oh, there's some internet problem. So you apply the zigzag relation on this part. On this part here. And what you get, you have this part can be replaced by a small straight line. You have A, and what you see like that. And what is that? This is exactly the left trace of A. So this is the proof of the first point. What about the second point? So this, which point I want to do? On the third point. Yeah. So the second point, I will leave the second point as an exercise about the direct do it as an exercise. So about the direct product, the direct sum. Now, what about the third point? How the trace deal with the tensor product? So for that, I will provide some hints. I will not prove that in details. In fact, in the book, nothing is proved. Everything is leave as an exercise. But here, so what about the third point? So the third point, so we leave that as an exercise. Okay. So what I want to do. Okay. So first, let us provide some hints of proof. So int 1. In fact, int 1, you should see you show that trace left trace of A tensor B is as follow. So the trace of A tensor B. So you have trace of A tensor B. So you should show that this is as follow. This is equal to the following. So you start from 1 and you apply the co-evaluation map of V. And then you get V tensor V star. And then you put some you put a 1 in the middle. You can always do that by applying what we call at the beginning of the course the isomorphism by the natural isomorphism about the tensoring by 1 on the left or on the right. Anyway, you can always put 1 here isomorphically, and then you apply IDV tensor co-evaluation W tensor ID V star, and what you get is V tensor W tensor W star tensor tensor V star, etc. So you continue like that. Here you will make the left trace of so you make etc. up to V tensor V star. So from here, so I need more room here. Okay. To V tensor 1 tensor V star. Here you will write So from here to here, you get the left trace of B. So you put everything in the middle. IDV, tensor IDV star. So that's why I put the point, because I don't want to write everything. And then you continue from here to go up to 1. As for the left trace of A. So what you get, and here, so from here to here, so let me write like that. Here to here, you should show that it is a co-evaluation map of the tensor W. So I rewrite it here. Co-evaluation map coev of the tensor W. So the coev of the tensor W, you should show that you can decompose like that, and when you are here, you focus on 1, and then you can develop the left trace of up to here. And then you finish, here you started the left trace of A, and you finish it here. And the point is here to show that this is exactly equal to that. So is equal to. This is the first hint. And the second hint is, in fact, and that will be, which is the left trace of A times left trace of B by the second hint. Because of the second hint is the following. So if you take, so let F in endomorphism, so morphism between from 1 to 1. So here, F is just the trace, the element between 1 and 1. Then the following commute. So let LV RV be the usual natural isomorphism. So 1 tensor V to V for LV, and V tensor 1 to V for RV. So the usual one we already mentioned. So the following commute. What commute? So you have V. You have V tensor 1. You apply RV. Or you have 1 tensor V. You apply LV. But here, here you apply identity of V tensor F. You come back to V tensor 1. V, same. And then here you apply F tensor ID V. And this commute. So this commute. So you should show that. Then show that. Show that this diagram commute. By showing that this diagram commute, in fact, what do you see? You see that you can switch. You can switch. Here you have V tensor 1, like here. But what we want one tensor V in order to put all the to put the part to distinguish the left trace of B from the left trace of A. In fact, I should write like that. This is commutative. But by doing that, you put the one on the left like that, and you put everything on the left, and then you get that. So this is the idea. Okay. So int 1, int 2. So I will not provide more details. And the fourth, so the last point was, how the trace of AB equal the trace of BA, how this property of matrix generalized here. So as we said, we need this star. So let us, this can be proved very easily with picture. Okay. So point number 4. So here, so let us start from that, and we will show it is equal to that. So trace, left trace of C double star A. So C double star. So you have C, and you took the double star of isomorphism. So this is a star, and the double star, you iterate this process. And this is C double star, and you compose with A. Here. And then you take the left trace. And so you see by zigzag relation again, zigzag. You apply the zigzag relation on here. So we apply the zigzag relation here, like that. So So let us go up to. Okay. You apply zigzag relation here, and so what you get is that. So you replace that by just a single, and you have C, A, and you do like that, and like that. So you see. Shorter. When you apply this zigzag relation, you get that, and you get this picture. Now you can apply again the zigzag relation, but on this part. And what you get is zigzag is exactly what you wanted. So C, A, you have the zigzag, and like that, which is equal to the left trace of AC. So you see, by picture, this is really easy. Okay, so it. Okay, so let us. So we leave the second point as an exercise. Left as exercise, but we will still provide a generalization of two. But in fact, because in fact, two deal with the direct sum. So the direct sum is you get the direct sum as a specific case of short exact sequence. The direct sum is a specific extension by short exact sequence. So, in fact, you can have something more general. As follow. So, proposition. So you start, let's see. So you need to be in a multi-tensor category. Let's see, be a multi-tensor category. So it's a generalization for multi-tensor category. You take two objects, VW in between V and V. I have no place. Right here, and you take a morphism in V and V double star. You take this such that W is a sub-object of V, and A of W is a sub-object of W double star. Then the left trace of A is equal to the left trace of A restricted to W plus the left trace of A restricted to the quotient. So if you prove this proposition, in fact, you get the point 2 as a consequence of this proposition. Because you can take a direct sum. In fact, you can take direct sum is a specific case of that. So proposition. In other words, the left trace is additive on exact sequence. And you have the same for right. Okay. So the int is the following. So use a filtration of V star tensor V induced by the short exact sequence this short exact sequence. So to be honest, in fact, I just rewrite the int as it is written in the book, but I did not myself make the exercise to prove this proposition. I have no time for that. I got no time to prove that. But anyway, it is not proved in the book, so it's fair, but at least it's an exercise to prove that. An exercise I did not do yet. But if you want to do this exercise, you can. So the exercise. Exercise. Prove it. The int is full. Okay. Now. What about now? Definition. Now we will introduce a fundamental notion in a monoidal category, the notion of pivotal structure. And in fact, this notion of pivotal structure will be really, in some sense, pivotal. It's really a pivotal, really important. So let C be a rigid monoidal category. So we will define it as formally, but we will also provide some picture for the intuition of that. Okay. So a pivotal structure. And in fact, it's It's a very fundamental structure because in fact, we don't know example of fusion category without pivotal structure. So it may be not an additional assumption, but maybe a property of fusion category, but we don't know how to prove that yet. So it's an open problem, very important. So a pivotal structure denoted A on C is an isomorphism. It's an isomorphism of monoidal functor between the functor identity and the functor double dual. So it's an isomorphism between these two functors. So what's the meaning of that? It's a collection. So recall the notion of monoidal functor, isomorphism between monoidal functor. It's a collection of isomorphism AX between so isomorphism between X and its double dual, such that for all X and Y in C, and for all F in for all morphism between X and Y. So what is Y? Yeah, for some Y, then so this monoidal, this pivotal structure is monoidal, so it's like that, and it's a functor. You have the functoriality like that. So I may write the functoriality like that. A Y composed with F is equal to F double star composed with AX, in other words, because isomorphism here. In other words, by isomorphism, F equal AY inverse compose F double star compose AX. So what about the picture? The picture for that. So let me check, in fact. So in the chapter about so where is it? Rigid. I just want to check whether for any rigid monoidal category, the double dual is isomorphic to X double dual is always isomorphic. Let me check. Rigid 42. Maybe it's only for tensor category. 42. Yeah, I guess it's true. X double dual is always isomorphic to X. Anyway, I have to check that because here you take an isomorphism. So I wanted to check whether at least that still always exists an isomorphism between x and x double star. But anyway, maybe, or maybe it's true for tensor category. I don't remember. So I'm a bit confused. So what about the picture? So you have x tensor y, x double star, tensor y double star. So you know, so this is pictorially like that. X double star, y double star, y. So these two pictures are equal, and this corresponds to this equality. Now, what about the other equality? In fact, we will use it. So F equal the double dual. So you have the double dual, and you have AX, AY inverse. So here you have X, here you have Y. So the equality, so pictorially, this is a picture for that. Yeah, this one. Okay, so so it's quite good. In fact, in a pivotal structure, with a pivotal structure, if you have something which is, you have too much something like that, you can replace it by the pivotal structure. You have something, etc. Okay, so I just wanted to note that here it's about this equality, not this one. Well, this is equivalent. Okay, so let me check something. We are in yeah. What I wanted to say is in the next section, let's see be a semi-simple multi-tensor category over a field, and let V be an object, then V is isomorphic to its double dual. So this is not true in general, but it's true for semi-simple multi-tensor category. Okay. So if you have a pivotal structure, you at least you have that for all. A weaker version of that. This implies that for every object is isomorphic to its double dual. But we will see in the next section that this is true for multi-tensor category, finite multi-tensor category. But I guess it's not true in general. So should be careful. Semi-simple multi-tensor category. Okay. Okay. But it should be okay. I guess there is a theorem saying that it's not always isomorphic to a double dual, but it's isomorphic to, you apply the dual sufficiently many times, and this will be isomorphic. See, Radford theorem or something like that. Okay, so what about next? So definition. So it's almost the end of today's session. Definition. So a rigid monoidal category C equipped with a pivotal structure is called pivotal. So it's a pivotal rigid monoidal category. It's an open problem whether any fusion category admit a pivotal structure or something like that. So I have no time for more. So I can just finish by this this remark. It is an open problem whether every fusion category, I don't know about admit a pivotal structure. We don't know all of fusion category without pivotal structure. So it's a fundamental open problem. It looks like the problem of our pseudo-unitary I mentioned, but recently we found something without pseudo-unitary structure. So maybe there exists a fusion category without pivotal structure, but you don't know one yet. What we know, what we will explain a bit later, but if you have a fusion category, or maybe a tensor category, but at least a fusion category, we don't know whether there is a pivotal structure, you can make a Z2 extension of the category called the pivotalization. And that provides a pivotal structure. So it's very close to a pivotal structure up to a Z2 extension. Okay, so I will stop here.